Okay, so we're talking about differential equations. We started with differential equations where we were just keeping track of what a certain population was doing over time. And maybe our equation said that the rate of change of that population maybe was proportional to the population. So then most recently, we started talking about systems of differential equations where rather than just keeping track of a single population, we have multiple populations to think about. So last time we did the SIR model where we're keeping track of the population of people who are susceptible, the population of people who are infected, and the population of people who have recovered. So we were juggling those three populations and thinking about how the rate of change from one affects the other. We're going to be doing a similar type of thing with this one. This is the predator-prey system. And so with this, we only have two different populations, the predator population and the prey population. And so this type of thing works for just about any predator-prey situation you might see in the real world. Things like owls and mice, lions and zebras, bunnies and lettuce. But we're going to be doing robins and worms, mainly because that's the same example the book was, and we're going to keep notation consistent. Okay, so we want to track what we think the population of worms is going to be over time, and what the population of robins is going to be over time. But in order to do that, we have to keep in mind that these things are going to be related somehow. So we want to come up with an idea for how we think these two populations affect one another, or more specifically affect the rate of change of one or the other. So we're going to start off with a simple case. We're going to start with this hypothetical saying, if there were no robins, what would the population growth of the worms look like? In other words, what is dw dt if there weren't any predators that were eating these worms? Well, as we've seen with our population growth ideas, this typically ends up being proportional to what the population was. So it's going to be some growth constant times that population of worms. So we're going to call that growth constant A, just because it's a convenient letter. So when there aren't any robins around, the growth or the rate of change of the population of worms gives rise to an exponential growth. We've seen this before. We typically call this K and P, but A and W works the same way. Okay, another hypothetical question would be, if there were no worms, as in if we only had a bunch of robins who didn't have any food, just want to go back and write down this was exponential growth. Right. If there were no if there were no worms, we only had robins, they didn't have any food, they're going to start dying off. And one way to model that is going to be exponential decay. And so what we mean by that is that the rate of change of the population of the robins is going to be still proportional to how many robins there are, but now we're going to have some negative number out front. And again, there's going to be some constant that we're going to call B that governs what this proportion is, governs how quickly this population is going to decline, but we're going to brush that under the rug for now. The point is that the rate of change of the robin population is going to be proportional to the negative of the robin population. Okay, so this is some hypothetical. This is the situation when the other population just isn't there anymore. What we really want to do is we want to take into account what the effect of the other population is going to have on a given one of these populations. In other words, the thing that I really want to know is dw dt when we're not necessarily assuming that there are no robins. So what is the rate of change of the population of worms when maybe they have this exponential growth going on, but they're also affected by the population of robins? So I'm going to say that it's A times W minus the rate of worms being eaten. Right, so the worms are multiplying, doing their own exponential growth thing, but then we also have the robins coming along and eating some of them. So that's taking away from this growth. So it's going to be whatever this exponential growth is minus how quickly the worms are being removed from the population. And so the question then is, what do we think this rate of change, this rate of worms being eaten, is proportional to? And the idea is that, well, if there are more worms out there, there probably are going to be more worms being eaten. And if there are more robins out there, there are going to be more worms being eaten. So this ends up being proportional to W times R. And I actually want to use different colors for these. So R. Okay, so I said that this was proportional to W times R. Again, we're going to need some sort of coefficient up from some sort of constant of growth. Let's just call that C because that's convenient. And this gives us the differential equation governing the rate of change of the worms. There's sort of two effects here. The population is growing because we have this exponential growth, and we also have this part that's taking away from it, maybe making it decline based off of how many robins are out there and how big the worm population is. All right, so this is our first equation. We also want an equation that tells us what dr dt is. In other words, we want to know how quickly the population of robins is changing over time, what the rate of change of this R number is. Well, again, this is going to do what it would normally do, so it's naturally going to decline unless maybe there's something else helping it along. So the rate of change of the number of robins isn't directly this rate of worms being eaten, but I claim that it's proportional to how many worms are being eaten. If there are more worms being eaten, that means the robins are doing better. This is going to be a positive thing for the rate of change of the robins or the robin population. So I would say that this number should be proportional to this other number. So rather than calling it dWr, because we already have some d's floating around, we're just going to call it k times w times r. And so again, the important pieces here are what these signs are, as in this term should be positive because this is an effect that's increasing the rate of change, whereas the other term might be negative because, well, the more robins there are, the more quickly the robin population is going to drop if there's no access to food. Okay, so this is our other differential equation. And in the next video, we're going to take a look at how we might solve these things.